Hey everybody, Mr. Troy here. I hope you're ready to do some function dances because it's time for Graphs with Mr. Troy. Yes, today's lesson is about graphs. Now, the awesome thing about a polynomial function is that you only need to know two things to know what its graph looks like. First of all, does it have an even degree or an odd degree? Second of all, is its leading coefficient positive or is its leading coefficient negative? Here's what you need to know. If you are looking at an even degree polynomial function, does it start with x to the 4th, x to the 8th, x to the 80th, x to the 88th? Okay, I'm getting ahead of myself here. If it does, then its ends will point in the same direction, whether that both be up or both be down. If it has an odd degree, x to the 1st, x to the 3rd, x to the 37th, then the ends will point in opposite directions, either upwards or downwards. The way you tell which way they go is based on the lead coefficient. So when the lead coefficient is positive, the positive end of the graph will be going upwards. So for this and this, we would know that they would have to have a positive lead coefficient. And you're going to know that by looking at the right end. Then the degree will tell you if the other side of the graph either follows for an even degree or goes in the opposition to that for an odd degree. If there is a negative lead coefficient, the right end of the graph will be facing downwards. Then you just pay attention to the degree to tell if the other end follows along with it or not. So a little bit of a reminder on arrow notation here. What arrow notation is going to tell you is what is happening on the left side of the graph. So if you were to travel along the graph towards x equals negative infinity, what is happening? And what is happening on the right side of the graph. So if we were to pick, say, for example, this graph, we would know that it has an odd power, so something like 3 or 5, and we would know that it has a negative lead coefficient. Now, this could be negative 5x to the 5th. It could be negative 1/10 x to the 77th. But here's just an example for you. Now, I know that this has an odd power or odd degree because the ends are pointing in opposite directions. And I know that it has a negative leading coefficient because the graph is heading downwards towards the right. So to put our arrow notation in, we say, well, what happens if we move along our graph from right to left, backwards of what we would normally do? Well, we would be going up towards the positive y's. So as x approaches negative infinity, y approaches positive infinity. The right side's a little bit easier. As x approaches positive infinity, the y values are decreasing, 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 decreasing. So y approaches negative infinity. So that's a bit about the lead coefficient test, end behavior, and also that arrow notation again. So I want you to practice that arrow notation. Can you write it for these 4 graphs? I'll pause the video, you pause the video, and then when we all unpause, the answers will just magically appear. Movie magic. Do pause the video though. Don't unpause it until you have those answers written down. All right, here's what I got for arrow notation. Now, to describe it in words, let's take a look at this one. The graph rises to the right and falls to the left. That's one way to say it. The graph is getting bigger as you're moving towards the right and getting smaller if you move towards the left. If we wanted to do this for an equation, we could say something like, the fact that this is of an even degree tells me that the ends point in the same direction. So, like this. This is what I was talking about with doing graph dances. The ends are going to point in the same direction. And I know it's like this as opposed to like that because we have a positive leading coefficient. So we have a positive or increasing right end. So the arrow notation for that would be, as x approaches negative infinity, y approaches infinity. And as x approaches positive infinity, y approaches positive infinity. Okay, next one. This tells us that the right end is going to point downwards. And because we have an odd exponent, the ends are going to point in opposite directions. So, something like this. My picture is not big enough. I'm trying. Where the ends are pointing in opposite directions, and to the one side, the graph is pointing downwards. I hope I did that right. Pointing downwards, pointing upwards. It's a lot easier when you're in a classroom. You can say that again. Okay, I'm going to fill in the arrow notation for the rest of these, and we can see how you did. All right, those are the 4 basic ways that a polynomial function's graph can look. Now, you'll notice we're only talking about the end behavior. What happens in the middle, the so-called wiggle in the middle, we don't know until we do a little bit more discovery. Okay, the next topic on graphs is called multiplicity. And you need to stay on this page. Don't fast forward because there's something new to learn here. So, multiplicity, we already learned that having a factor repeated yields what's called multiplicity, which means it counts twice for the fundamental theorem of algebra, or 3 times or 4 times. But there's another rule that we need to learn. So when you are looking at a function, if it's factored like this, you can tell what its zeros are going to be. So for example, for this one, I can see a 0 at 1, a 0 at 3/2, and a 0 at -4. I can tell that this is has a positive leading coefficient, and I can tell that it has 1, 2, 3, 4 zeros, so it is an even degree. So it has to point upwards towards both ends. Now the thing that's new here is that if a 0 is repeated an even number of times, the graph is going to bounce off of that 0. If a graph is repeated an odd number of times, if a 0 is repeated an even number of times, the graph will bounce off that 0. If a 0 is repeated an odd number of times, the graph will go through the axis at that 0. So that's going to lead to a graph that looks like this. So the graph goes through the axis at these zeros, the zeros that are only in the factored equation once each. And the graph bounces off the axis at this 0, 1, because its factor is repeated an even number of times. The place where we first came across this idea was when we were learning about inequalities. We know that a graph can only cross the axis at a 0, but if that factor is repeated twice, then it's going to have the same positive or negative sign inside the parentheses. And here's what I mean by that. It means if I pick an x value, say for example I pick 0, and I plug that in, I'm going to have two negative sets of parentheses, a positive set of parentheses, and a negative set of parentheses. So 3 negatives altogether, which is why I'm under the axis. Now, if I go to plug in something like 1.1, I'm going to get a positive, a positive, a positive, and a negative. So still multiplying out to be a negative. Since these two signs change with each other, they don't allow me to go from negative to positive because they are an even number of, they are happening an even number of times. Okay, so looking at our next one. Remember, this tells us that we have a 0 at 0, and this tells us that we have the same 0 at 3/2 repeated 3 times. So here's 3/2, here's 0. This graph has a positive leading coefficient. If we multiplied all of this out, our leading coefficient would be 8x to the 4th. So we're going to go through our graph here, and then when we have a value of 3 for our multiplicity, our graph won't go straight through our 0. It will make a little squiggle through the 0, but it still will pass through it. It'll just change its shape a little bit. Okay, so I want you to pause the video and give these a try. See if you can do this. Okay, and then we will go over this tomorrow as part of our warm-up. So an example of how this ties into taking an equation and making a graph is that it now gives us more powerful information once we say factor. So if we factor this and see that it is x plus 5 quantity squared, all of the sudden I know my graph hits the x-axis at -5 but bounces off, and I know that the ends both point in the same direction and upwards. So to make sure all of that's clear, bounces off because the factor is repeated twice, pointing upwards because we have a positive leading coefficient and an even degree. So that makes life way easier. If I take a look at the next one, and I factor that, I can factor to x squared times x squared minus x minus 20. or x squared times x minus 5 times x plus 4, all of a sudden I know tons of information about this graph. Sure, before I knew what the zeros were, but I didn't know that bouncing thing. I mean, I did. You might not have. I'm the math teacher. Graph not to scale. So this graph has to end up with both ends facing upwards, again, because just like the last one, it has an even degree, and it has a positive leading coefficient. It has to cross through the zeros at -4 and +5, but it has to bounce off the 0 at 0 because of the even multiplicity. So suddenly we know tons more information about our graph. It would allow us to do our polynomial inequalities much more easily than having to plug in test points. All right, so finally, we'll put this into practice. We'll look at one graph. I want to summarize everything we know so far. So far we know that the ends point in opposite directions. That's because the degree is odd. It's a third degree function. We also know that the right end has to point upwards because the leading coefficient is positive. Furthermore, we know that this graph has 3 zeros, but at most 3 real zeros. It could have a real 0 and 2 imaginary zeros. And we know that this graph has at most 2 turning points. That's from like the very first lesson. So n number of roots and n minus 1 turning points. We also know that this graph is going to have its y-intercept at -4 because that's the constant term. And get this, we know that the domain is all real numbers because there's nothing you're not allowed to plug into a polynomial. And because the ends have to point in opposite directions, we know that the range of this graph will be all numbers too, because if the ends are pointing in all directions, then the graph can go all the way up and all the way down. So that's all stuff I can know without ever picking up a pen or pencil. From there, the other thing that I know is that this factors by grouping. We actually talked about this in class today, if you were there. And if you weren't there, how would you know what day today was? That this factors to x squared times x plus 1 minus 4 times x plus 1. So this factors by grouping, and then I can say, okay, so x squared minus 4 times x plus 1, or finally, x plus 2 times x minus 2 times x plus 1. So let's put that information on there. We've got an x-intercept of -2, an x-intercept of -1, and an x-intercept of +2. We have a y-intercept of -4. So from here, all we need to do is plug in a couple of different points, and we'll have a great picture of our graph with very little work. If we plug in just these 3 points, we will know pretty much what is going on with the rest of the graph. Okay? We would probably want to do that using synthetic division because it's the easiest. But if you're comfortable cubing numbers, then you can definitely do that as well. So I plugged those in, and I got -3, -10, 1, -6, and 320, which is way off the top of my graph. So that tells me that my graph looks something like this. Now, there is a little bit of motivation for future study here, and that's this. You know that the graph has to go through the axis at both of these zeros, which means that there has to be a maximum somewhere in here, but it is not at negative 1.5. In order to know where it is and why it is, that's when we need to use calculus. So as to where exactly this is, you could guess by plugging in negative 1.5 and get very, very close to it. But in order to figure out exactly where it is, you need to use calculus, which is why we're here, so that someday we can use calculus. All right, everybody, I hope you're hanging in there. Make sure you're doing your homework. Make sure you're staying hydrated. Make sure that you're getting plenty of rest. Make sure that you're telling lots of good math jokes. I didn't have a last one there. I'm sorry. All right. This has been another episode of Graphs with Mr. Troy.